Look at almost any rooftop fitted with solar panels and you will notice something that nobody ever really questions. They are blue. Not painted blue, not dyed blue, but this deep, rich, almost metallic blue that has become one of the most recognizable visual signatures of the renewable energy era. Drive through any suburb, scan any commercial building, zoom into any aerial photograph of a solar farm, and that color is everywhere. But here is what most people never think to ask. Why that color? Is it a branding decision? A manufacturing coincidence? Or is there something happening at the level of physics and material science that makes blue the natural outcome of turning sunlight into electricity? The answer turns out to be far more interesting than most people expect, and it starts with an element so common that it makes up roughly 28% of the Earth's crust. To understand why solar panels look the way they do, you first need to understand why anything has color. Sunlight is not a single thing. It is a mixture of wavelengths, each one corresponding to a different color in the visible spectrum. When light strikes a surface, some of those wavelengths are absorbed and some are reflected back toward your eyes. The wavelengths that bounce back are the ones your brain interprets as color. A tomato looks red because its surface absorbs most wavelengths and reflects predominantly red light. Grass looks green because it reflects green wavelengths while absorbing the rest. Solar panels are engineered to do the opposite of almost every other colored object in existence. Rather than reflecting light, they are designed to absorb as much of it as possible, because every photon that enters the solar cell is a potential electron, and every electron is potential electricity. But no material science is perfect. Even the most carefully engineered solar cell still reflects a small fraction of the light that strikes it. And the particular wavelengths that escape, the ones the cell cannot quite capture, are what give the panel its visible color. For decades, that color has been blue. The active material inside almost every solar panel ever manufactured is silicon. It is a semiconductor, meaning it sits in an interesting middle ground between a conductor like copper and an insulator like glass. When photons from sunlight strike a silicon atom with sufficient energy, they knock electrons loose from their atomic bonds. Those freed electrons are then guided through the material by an internal electric field, creating a flow of current. That current is electricity. Pure silicon on its own has a dark gray appearance, but it has a significant optical problem. Bare silicon is surprisingly reflective. Without intervention, a significant portion of incoming sunlight simply bounces off the surface before it ever gets the chance to interact with the material underneath. To solve this, manufacturers apply an extremely thin layer of a compound called silicon nitride across the surface of each solar cell. This layer is so thin that it is measured in nanometers, fractions of a thousandth of a millimeter, and its thickness is not chosen arbitrarily. At that specific thickness, something called destructive interference occurs. Light waves reflecting off the top surface of the coating collide with light waves reflecting off the bottom surface, and because they are slightly out of phase with each other, they partially cancel one another out. The result is a dramatic reduction in overall reflection, which means more light entering the silicon and more electricity being generated. But here is the detail that explains the color. This destructive interference works more effectively across some wavelengths than others. Red and green wavelengths are suppressed more efficiently than blue ones. The blue wavelengths that remain are the ones your eyes detect. The panel is not blue because anyone chose blue. It is blue because blue is what is left over after the engineering has done its job. If you have looked at more recently installed solar panels, particularly on newer homes or premium commercial buildings, you may have noticed that many of them appear almost completely black rather than blue. This is not a coincidence, and it is not purely aesthetic. It reflects a fundamental shift in the manufacturing technology behind the cells themselves. Traditional blue panels are made from polycrystalline silicon. During manufacturing, molten silicon is poured into a mold and allowed to cool. As it solidifies, multiple silicon crystals form simultaneously and fuse together, creating a structure full of crystal boundaries. These boundaries scatter light in multiple directions, and combined with the silicon nitride coating, they produce that characteristic shimmering blue appearance. Newer black panels are made from monocrystalline silicon. Instead of allowing multiple crystals to form randomly, manufacturers grow a single large silicon crystal through a slow, controlled process and then slice the solar cells from that single crystal. The result is a far more uniform internal structure with far fewer boundaries to scatter light. Combined with improved anti-reflective coatings that suppress reflection across a broader range of wavelengths, monocrystalline cells absorb more of the visible spectrum overall. Very little light escapes reflection, which is why they appear nearly black. A common assumption is that black panels must be dramatically more efficient simply because black surfaces absorb more light. The reality is more nuanced. Color is a byproduct of the optical and material engineering, not the primary driver of performance. Monocrystalline panels are generally more efficient than their polycrystalline predecessors, but that advantage comes from their superior crystal structure and improved manufacturing precision, not simply from appearing darker. If researchers discovered tomorrow that a panel engineered to appear bright green or deep purple could capture more usable energy, the industry would adopt that color without hesitation. The visible color of a solar panel has always been a consequence of the physics rather than a cause of it. So the next time you look up at a blue rooftop and wonder why solar technology settled on that particular shade, you are really looking at the visible signature of destructive interference, silicon chemistry, and the specific wavelengths that an anti-reflective coating could not quite suppress. Not a design decision, the physics outcome.